Hello, pre-matriculants, and welcome to This is Learn Extra Live with me, AB, Abram, and John. How are you, Mr. John?
I'm really well, thanks, Abram. It's really good to be with you again, grade 11s, and I'm really excited about this particular lesson. We're carrying on from what we've been doing over the last few weeks, and we're going to get into some stuff that's really important, because up until now, it's been stuff that's coming up in the final exam. So this is no longer pre-matriculation. This is the real thing. So make sure that you get down those notes. Abram, where can they find them?
I like that, John. This is the real thing, and of course, it is a Women's Month. Before I tell you all about that, we just want to say salute to all the women of South Africa with John.
Absolutely. Now, I'm not a woman. You can see that. I hope you can. But absolutely, we really want to support the women, and we want to wish everyone a really fantastic National Women's Day on Friday.
On Thursday.
No, it's on Friday.
On Friday. Oh,
hey, long
what
weekend.
happened to me?
What do you
like,
know?
I'm thinking it's Monday.
No.
Okay. Yeah.
Forget it. He's half asleep today. He's making some silly statements. But just let's get on.
Let's just stick to learning what we do best. Mindsetters, get your notes on Learn Extra Live. Learn Extra Live. LearnExtra.co.za/live, or else you can chat to me on Facebook. I love Facebook. I'm here for you on Facebook today. Facebook.com/LearnExtra. Thank you very much, Sean.
Hey guys, you've got to help me here. Abram's falling asleep. So you better chat to him.
I need some energy.
He needs some wake-up call. Hey? So wake him up, please, and we'll get on with our son.
Electrical shake.
Yeah, some shocking news for him. Eh? So let's do this lesson. We're all about shocking. We're about electrical calculations, and this shouldn't be too much of a shock for you, because we're going to be doing some examples of circuit problems. Now, you've been doing circuit problems since what, grade 5, 6, 7, all the way through. Well, yeah, maybe you have. But these ones have a little twist in the tail. So you need to concentrate, you need to be careful, you need to follow some important principles. Now, before I get started, what I want to remind you is last week we did Ohm's law. Previous week we did electromagnetism. Last week we also defined current and potential difference. We're going to use all of those formula, as well as power, to calculate circuit problems. But what's another thing that's really important for you to understand is that there is more than one way, in most cases, to do a circuit problem. But you've got to have a strategy to solve it. So let's set that out. Today we're working through different circuit problems, and I just want to recap those formulae. So we looked at these formulae last week. Remember that we said that current is I, and it is measured in amps, and that's the defining equation, where I is equal to Q divided by T, delta T, the charge measured in seconds, and the time is measured in seconds, and the charge is measured in coulombs. Now, in this case, most of the time you're going to be dealing with coulombs, not millicoulombs or microcoulombs. If they happen to give that to you, you'd have to convert it to the SI unit. Now, let's move on. We spoke about potential difference. Potential difference, V, is measured in volts, also V, so don't get those two mixed up. W is the work done, or the energy used up, and again, we've got the charge. It's per unit charge, so the Q is the same Q there. Now, Ohm's law is this expression, this one. We showed it last week, and we said R is equal to V over I. So that's the relationship. Potential difference and current are directly proportional. The resistance is constant at constant temperature. So we need to take note of that. Now, in a circuit, we also said that if you've got things in series, you can add the resistors together. But when they're in parallel, you need to do 1 over the parallel section. And then the last few formulae that we ended on last week were the power formulae. So we said power, which is the rate at which work is done, or the rate at which energy is dissipated or used up in an electrical appliance. Okay? that is equal to the V times I, or the I squared times R, or the V squared divided by R. Now, guys, those formula are incredibly important. But there's one other concept that I want to just go over, because it comes up so often, and we're going to see it in almost every one of the problems that I've selected for you. And that's the difference between something called EMF and the external voltage, internal voltage. So we need to understand, when we were doing electromagnetism, we said the moving the magnetic field induced an EMF. So what's this EMF? Well, in a circuit, EMF stands for electromotive force. I'm not going to write it out, but it's given a symbol E. And in a circuit, it really refers to the maximum potential a cell or battery can deliver. So if you look on the bottom of, or on the side of a normal cell, one of those things that you put in a torch will work. It says 1,5. That's the EMF. It doesn't matter if you've taken it fresh out of the package and it's just come from the factory. It has an EMF of 1,5. But you know, you put it into the torch for a while and you go hunting around in the dark, then that potential difference, that amount of energy that the battery or the cell is able to deliver, doesn't stay at 1,5 for a long time. It slowly decreases because there's internal resistance. Okay? Because there's chemical reaction happening inside that cell that makes it more difficult to deliver the push around the circuit. Okay, so we need to understand that this is the maximum. So in a circuit, what we do is, if we have a simple circuit and we put a couple of cells together here, and we're going to say, let's have a switch over there, and we'll just draw the switch in like that, and we have a resistor over here, and something like that. I just want to get an ammeter as well, so I'm going to erase that, go back to there, and I'm going to put my ammeter in. I'm now going to say to you, if I take a voltmeter reading across here, like that, with the switch open, guys, what's going to happen? Well, the battery of the two cells, remember, this cell here is positive, that's the negative terminal, this is positive, that's negative. So it's a battery of two cells connected in series. This voltmeter is reading the maximum potential because it's on open circuit. The circuit is open. It's not doing any work. So I want to tell you a story about Abram over there. And I know he'll forgive me afterwards, but we'll just get a little story for illustration point of view. Abram went for one of those special evaluations when somebody, like, they can't really do this, but just imagine for a minute. They could measure his potential. Wow, it's off the scale. He did one of those special psychometric tests. It was off the scale, such a high reading. Okay? Because he didn't have to do any work. Okay? He didn't have to do any work. Because on this thing, it's the EMF. There's no work done. Please note, no work. The reason I can say there's no work is the current here is 0 amps. Okay, so now here comes the story. What happens with this very high potential? Now, Abram has to go and put this potential into action. So what we do, instead of the battery there, we're talking about Abram now, and we're saying the same thing about the battery as we say about Abram. Let's take a look at what we've got here. We've got a scenario. Now, same two cells. I'm just drawing them over. There's the ammeter. There's the resistor. Oh, the switch is now closed. Notice, the switch is closed. The voltmeter reading now is no longer reading the maximum potential. I want you to notice something here. This is a closed circuit. It's a closed circuit. And that means that the battery has to deliver current. So I don't know how much current there is, but what I know is that this current over here is going to be greater than 0. It's not going to be 0, it's going to be bigger than 0. It's got to deliver to the circuit. In other words, there's work is being done. Work is done in the external circuit. So energy from these little charges that are moving around here is being not used up. It's not used up yet. It gets to the, there it's used up. Now on this side, it's got less potential. Over there it was full. The potential energy that it was carrying, it had lots of potential energy. But now, over on this side, these little charges, they no longer have lots of potential. They're only half full. Okay? Now, they're half full. They've been used up. Why? Because they had to get through this resistor. That was hard work. Work had to be done. So now, when this little battery, this little charge, which is carrying along a little potential, comes back, the voltmeter reads the difference in potential. It says, you had maximum potential over here, maximum there, you've gone down. So this no longer reads EMF. This reads the potential difference of the external circuit. It reads potential difference, in other words, in the external. It's no longer full. It's no longer maximum. And the reason it can't be maximum is because it's being used up and because this little charge has to get from here to there. And it's got to refill. Now, in that process, in between there and there, there is something called an internal resistance. Internal resistance. And that's given a little symbol R. So, here's the scenario with Abram. Remember, he had maximum potential, off the scale, amazing stuff. We put him to work and we say, there's the task to do. And you know what? He can't deliver. Why? Because there's internal resistance. Because at the back of the ranch, Abram's thinking, I wouldn't like to be working. I'd rather be twiddling my thumbs. No, that's not really it. Okay? You'd rather be listening to music. No, that's not really Abram. But do you understand what I'm saying? Sometimes there's internal resistance. We could be doing 100 different things, and we don't reach our maximum potential. Okay, so Abram, enough teasing for the moment. But I hope you understand, guys out there, that on a closed circuit, we're no longer measuring EMF. So what's the relationship between EMF and the external resistance? Well, I need you to understand that there are two parts of where work is done. So EMF is the total, this is the maximum, and then what we're saying is there's work done in the external circuit and there's work done in the internal circuit. But V is equal to I times R. So I times R external plus I times little r, the internal resistance. Okay? So I just want to erase that little sign there and put it back. So there we go. I times little r. You got that? We could factorize that and we can get I times r plus little r. And that's the equation that you'll see on the data sheet. Please make sure you understand this concept of internal resistance, EMF, and potential difference. And don't forget, don't be lazy, achieve your maximum potential.
Can I ask something, John?
Yeah, sure.
Does this mean rechargeable batteries have EMF?
Yeah, even rechargeable batteries have EMF, okay? And even with the rechargeable batteries, and that's another section of the syllabus, it's more in chemistry. In grade 12, you'll deal with batteries. Okay? What we recognize there is that they can still have an EMF because they will have a maximum potential, but they will over time build up a chemical deposit that will not allow their potential to be as maximum as it was when they were first used. Okay. Does that answer your question?
Yes.
Okay, cool. So, guys, keep this in mind. Make sure you revise it. It's going to come up. Let me show you where. So, here's the first question. We are given, have a look at it, a simplified circuit diagram represented alongside shows part of the electric wiring of a model doll's house. Okay? I just want to make sure that you've got it. And we're saying bulb B and a fan F are connected to a 12-volt car battery. The internal resistance, remember what we said that was, of the car battery cannot be ignored. Okay? So there's the circuit diagram. Little battery. There's switch 1. There's the bulb. There's switch 2. There's the fan. It's represented as a resistance. Now, look what it says. The bulb is rated 12 volts, 15 W, 15 watts. That's the power. When the switch S1 is closed at maximum voltage, the bulb allows a maximum current of 1,25 amps to pass through it. Calculate the resistance of the filament. So in other words, all that we're doing in this first part of the question is we're saying, let's close that switch. So now we've just got one bulb, one light bulb, one battery, and there we go. And you're asked to calculate the resistance of the switch. Well, I think it's quite simple. The second part is one for you to think about. Both the switches are closed. The bulb glows a little dimmer. Explain fully why the bulb glows dimmer. Now, guys, you've read the whole question. I hope you've downloaded it in your notes. And I think it's time to give you the chance to see if you can do some calculation. So you try and work it out. Remember everything that I've said. And let's see you after the break.
And it's there on Facebook also, Mindsetters. If you not on Facebook, log on to Facebook and then like our page if you haven't. It's facebook.com/learn extra. We'll see you after the break. Don't you dare move. Welcome back, Mindsetters. Now, I hope you're all up, chilled, learning with us. Tiwana says on Facebook, as we were talking earlier on about internal resistance, he says, the whole purpose of education it is to remove an empty mind and actually put something on that mind with an open one. So talking about internal resistance, you should actually remove that and put something on it.
Yeah, absolutely. So guys, but remember this, and it's an important idea. When we talk about teaching and we talk about concepts building in science, nobody comes to the science classroom without any knowledge. You've got knowledge because you've got observations from all around you. You need to apply that. So be imaginative, be creative. You can do it. Be motivated. Okay, so how did you do on this problem? I hope you've got it, but let's check it out. So the first part of the question, part A, we were asked to calculate the resistance. Now, if you remember the formulae for resistance, then the most obvious one is R is equal to V over I. So that's Ohm's law. So as soon as you've got a question about resistance, why not use the easy one? Don't try and make life difficult. It's only the resistance of one resistor. So we're not talking about connecting things together in series or parallel. There's one switch open, and it's a series circuit. And so we're really interested in V and I.
Remember, John, you asked the Mindsetters.
Yeah.
And they gave some answers, and they say, you know what, there's just no need for you to do this question. They understand it. So they gave us some answers. So you're going to prove those answers right.
Yeah, we're going to prove them right. So let's just make sure, because there's some people that might not have given answers. So, guys, have a look here. 12 volts and current of 1,25. So what are we going to do? We're going to substitute in to this equation. We're going to say 12 volts. Now, notice that this one said are connected to a 12 volt battery. The internal resistance cannot be ignored. So at this point, we cannot ignore the internal resistance, but what we're told over here, the bulb is rated 12 volts, and the current is a maximum at 1,2. So we're going to take that value there. We're going to say 1,25 amps, and we're going to take that as the current passing through the bulb, and we're going to expect that that's the maximum resistance. This might not be what actually happens in the circuit, but that's what the bulb is made to do. So let's see. 12 divided by 1,25, and we get an answer of 9,6. Now we can't just leave it as 9,6. We must say what the units are. So we're going to say 9,6, and its resistance, so it's ohms. And there we've got it. Okay. Now, bear in mind that that's what the bulb was built to take. It didn't say that's the actual potential difference across it. It says it's rated at 12 volts, 15 watts. Okay? It says when we adjust the circuit, it's got a maximum, allows the bulb to have a 1,25 maximum current. So what's the resistance? And we've used that detail. Now, the next part of the question says these two switches are closed. So now I want you to watch carefully here, because this is very, very important. So now what we've got is we've got this situation, this scenario. We've got that, and that is closed. So I hope you can see that this forms a parallel branch. Now, guys, understand this. Even though we've added the fan into the circuit in parallel, the total or equivalent resistance in a parallel branch will be less than the smallest resistor. Let me say that again. The total resistance, or the equivalent resistance, and the way we work it out is 1 over R is 1 over R1 plus 1 over R2. But this equivalent resistance will be less than R1, and it will be less than R2 on its own. You've got to understand that. When you put things in parallel, it lowers the resistance. Now, from Ohm's law, go back here. If we lower the resistance, then what's going to happen to the current? If the resistance gets lower, then you've got to see that there's going to be a change here and there's going to be a change here. So it's very important that you understand this. If we've got a smaller resistor, that means that more charges can flow through it. Now, if more charges can flow through it, so if we decrease resistance, this is the important part. So because we put it into parallel, resistance of the external circuit decreases. Okay, that's the first point. Second point, if the resistance decreases, the current that's going through the circuit, and it's in series, so it's the total current, actually increases. Wow. Guys, you've got to follow this very carefully, because it's important that you follow this. Okay, now the next part that you've got to see is if the current is increasing, that means it's increasing critically between the battery. And that means that resistance is going to have an effect. So the V internal which is equal to I times little r. The little r doesn't change. The I has got bigger, remember? So this part increases. So now remember something. Remember what we said earlier. And you've got to follow this through. We said that EMF is equal to V external plus V internal. Now remember that this is a maximum. It can't change. If we do this and we make this one bigger, this gets bigger, then what has to happen? Abram, help me here. If this gets bigger, then what has to happen to the green one? This, so this was this plus this is equal to that. That can't change.
Mm-hmm.
This one gets bigger. What has to happen to this? Come. If we've got, let's do it in simple terms. If we've got 6 sweets, and you've got 3, and I've got 3 to start with.
Mm-hmm.
Okay? That makes 6.
Yes.
You with me?
Yes.
But now, because I'm hungrier than you, I've now got 4. We've still only got 6 sweets.
Mm-hmm.
I've got 4. What's happened to your share?
They decrease.
It decreased.
Yes.
So if this one got bigger, then the external one will get smaller. You got that?
Yes.
So what we're saying is the V external gets smaller. Now guys, there's your explanation. What we had to say is explain why the bulb grows dimmer, a little dimmer, just a little bit dimmer. Well, if the V external gets less, then that means the potential difference across the bulb is going to decrease. That decreases. And the brightness of a bulb is related to the power. And power is V squared over R. Now, if this one has got smaller, that's got smaller, the resistance is constant. So what's happening to the power? Remember, power is brightness. Do you see what's going to happen? If this gets smaller, then you've got the same number, then the power is going to get less. The brightness is going to get less. It's going to get dimmer. So guys, think it through and make sure that you follow. If you change anything in the external circuit and you can't ignore the internal circuit, internal resistance, it's going to have an effect on the whole circuit. Please try and get the balancing right. Okay, it's a very important principle, and it's a question that's often asked. When you change from series to parallel, you are changing the external resistance. If you decrease the resistance, you increase the current. Make sure you've got that. Okay, let's move on. Abram, we've had enough on that particular question, so let's go on to the next one. And we don't want that, so let's go on to this one. It says, you'll notice here that there's a common theme about internal resistance. In the circuit represented, each cell, here's a trick. The examiner loves this. They try to tell you what happens in each cell. Check the diagram to make sure you're working with what happens to the battery. Okay. Has an EMF of 1,6 and an internal resistance of 0,25. Now, before I carry on, I'm going to notice that that's one cell and that's 2 cells. So I'm going to say the EMF of the battery is not 1,6, but it's 1,6 times 2, which is 3,2 volts. And the R of the battery is 0,25 times 2, which is going to be half an ohm. So I'm just doing that so that I know where I am. I'm not going to fall into the trap. So it says 2 resistors of 10 and 30 ohms are connected in parallel, and the ammeter is connected such that it measures the circuit current. Circuit current means the total current. So there it is. It's going to measure the maximum current, and we can see it could be, it's in this part of the circuit, before the branch and after the switch. So it's not in the parallel section. This is reading I total. Okay. So the switch is open on the following. What is the reading on the following? Okay, so here we go. With the switch open, what's this reading? We've done it already. This is EMF. And what's the EMF? We've worked it out. I've worked it out up there. EMF, the voltmeter is going to read 3.2 volts. What's the ammeter going to read? Well, remember, when you've got an open switch, no current can go through. If the switch is open on this side, doesn't matter. It's not going to go through like a cycle. Only on a closed switch will you get a current flowing. So the current here, the I, is going to be equal to 0. 0 amps. Okay, you got it. Let's move on, because I think we've got time just to do the next part of it. And it says now the switch is closed. So guys, let's just write down the values that we've got. We know that EMF is 3.2 volts. We know that the internal resistance was 0.5 for the battery. And we're now told this switch is closed. And the first part is to say, calculate the effective resistance of the combination of resistors. So I'm just going to quickly do that part and see if we can get through it. We've got look here, that's where the current is going to divide. Some of it's going to go there and some of it's going to go there. Some of it's going to go down there and some of it's going to go down there. So this section is in parallel to that section. How are we going to work it out? Well, I'm just going to do it on the side here so you can see. 1 over Req is equal to 1 over R1 plus 1 over R2. And we'll write that as 1 over 10 plus 1 over 30. Now, don't make a mistake. Don't try and only do it in your head. You can check it on the calculator. 30 is the lowest common denominator. 10 goes into 30 3 times, and 30 goes into itself once. So the 1 over Req is 4 over 30. But is that Req? No, it's not. You've got to write down, and I'm just going to put it in over there. Therefore, Req is equal to 30 divided by 4. Now, quickly, let me pick up the calculator and make sure that I haven't made a mistake, and you can check me and see my answer is right. So I could use the fraction button, and some of you might prefer to do that. You could say 1 and then put the 10 at the bottom, and then go out and say plus and put the fraction button again, and we're going to say 1 on the top line, and on the denominator we're going to say 30, and then we're going to say equals. And there it gives it to us, 2 out of 15, which was the same as what we got. If I wanted it, that's not the answer though. So please remember, we said 4 out of 30, 2 out of 15, we've just cancelled down. That's not the answer. What I really want is the inverse. And the inverse button is over here. So if I say inverse the answer, and I get an answer there, it's 15 over 2, which is the same as 30 over 4. And if I give the answer, it's 7.5. So let me write that down. 7.5 ohms. And we've got the answer for the first one. Right. Let's look at one more, and then I'm going to ask you to do it during the break. So if we know it's 7.5 ohms, during the break, why not calculate the reading on the ammeter and calculate the reading on the voltmeter? Remember, the ammeter is over here, and the voltmeter is that one. Remember, the switch is closed. See if you can get the answer. Abram.
Well, let's see if you can get that answer, and then we'll check it after the break. But in the meantime, do the question. We'll see you after the break. Welcome back, Mindsetters. Now, if you just joined us now, you're a bit late, very late, but you can still download our notes on learnextra.co.za/live. Otherwise, check us on Facebook because we have the questions also posted on Facebook. Our Facebook is facebook.com/learnextra. John, take it away.
Right, guys. How are you doing with that question? Well, I hope you've got it. Let's see how we're going to answer it. Now, look what we're trying to do. We're trying to find the total current. Remember, I total is set up through this ammeter. So I don't know too much about total current. What I've been told is I've got a whole lot of stuff about EMF, and if I've got EMF values, I've got an EMF of each cell being 1,6 and an internal resistance of 0,25. So what I'm going to do here, it's not like I've got a voltmeter and an ammeter reading and a resistor. So I can't really use Ohm's law here. Because I've got EMF, I'm going to have to use that EMF equation I showed you. And so that's exactly what I'm going to do. So what I'm going to write down is I'm going to say, I know that E is equal to I, the total current, times the external resistance plus the internal resistance. Do I know the external resistance? Yes, I've just done it. I've just worked out, that this part of the circuit that I'm going to box here can be replaced by a 7,5 ohm resistor. I know that. There's nothing else that's giving resistance other than this little r here. So I can't ignore that little r. Remember that little r was 0,5. Now there was a question on Facebook and said, why did we multiply it by 2? Remember the question said each cell. So each means that there are two, and the diagram shows you two little lines. Every one, that's the positive, that's the negative. That's one cell. That's the positive, that's the negative. That's the second cell. The cell is like a battery. When you put it together, it makes a bigger battery. Okay? What we call a battery in everyday life, the thing you put into a torch or into a CD player, one of those little 1,5 thingies, that's called a cell. When you put them together and you connect them, you make a battery. So that's why we've doubled it. So we're going to use those values, and can you see what we're missing? The only thing that we're missing is the total current, and that's what we want to find. So I'm going to substitute in, and I'm going to say 3,2 is equal to I, the thing I want to find, 7,5 plus 0,5. And when I add those two together, I'm going to get I is going to still stay in brackets, 8,0, and 3,2 on this side. Now, what's that going to give me? Well, I can do it in my head, but it's better to check on the calculator. So let me do that. I'm going to say, clear the calculator, 3,2 divided by 8, and I'm going to get 2/5, which is 0,4. Okay, 0,4 is my answer. So my total current, therefore, I is equal to 3,2 divided by 8, which is equal to 0,4 amps. Don't forget the correct sign. So now, people, what we need to do is we need to find the reading on the voltmeter. The reading on the voltmeter is not the EMF. It's not that thing. Okay? The reading on the voltmeter is this thing here. So that's not difficult to work out. And we can see, because it's I times R. Substitute in 0,4 times the resistance, which was the external resistance, 7,5, and we're going to work it out very quickly using the calculator. So there we go, 0,4 times 7,5. Let's just delete that part because I want to make it 7,5. Okay, and we get an answer of 3 volts. So look here. 3 volts is going to be used up in the external. So the total was 3,2. Internal is going to be 0,2. External is going to be 3,0. Can you see how these balance each other? And you've got to make sure that you follow that from the equation that I've shown you. Okay. Right, let's move on. Question 3. It says Peter sets up the following circuit. He uses a battery with an EMF, danger, EMF, be aware, think about internal resistance of 12 volts. The internal resistance is so small that it can be, you can ignore its effect. Sure, we can forget it. It's just the same. It's now, if we have the equation, we could say E is equal to V external plus V internal, which is equal to I times R plus I times little r, and we just cancel that out, and we say that's where we are. We're just looking at that one. Okay? We're ignoring the the internal resistance. His circuit contains 4 resistors, an ammeter and a switch. The diagram shows the values of the resistors. He then closes the switch. Now, what does it say? Calculate the total resistance of the circuit. Now, guys, for this thing, the important part here is to know your circuit. Understand where things are in series and where they are in parallel, and then you can apply your formula. So, very quickly, what I want to do is I'm going to start at the battery, at the positive terminal, and I'm going to mark everything where there is one current, because those parts are in series. So I start at that terminal, and that part, and that part, and that part. That's in series. So if a battery is in series, in the series part of the circuit, I can add its resistance together. If it's in parallel, look here. This, the current divides, and one part goes that way, one part goes that way. So there, these two 4 ohm resistors are in parallel. I want to get the total. I best work out what the R equivalent is. 1 over R equivalent, 1 over R1, plus 1 over R2. And I'm just going to say it's 1 over 4 plus 1 over 4. And that's going to give me 4 over 1 quarter plus 1 quarter is 2 quarters, which is going to give me a half, first of all. Therefore, R equivalent is equal to 2 ohms. So I'm going to replace this whole thing by one single 2 ohm resistor. Now I can work out the total, and I can say R total is equal to R1 plus the branch, or the equivalent, plus R, what was this? If that's 1, that's 2, that's 3, this is 4. Okay? So if I do that, R1 was 3 ohms, plus 2 ohms for the equivalent, plus 3 ohms for there. It's a little untidy. 3 and 3 is 6, and 2 is going to be 8. So 3 and 3 is 6, and 2 is 8, and there we go. The total resistance is 8 ohms. Now, calculate the reading of the ammeter. Very nice question. So, and it's a very common question, so let's make sure that we get it right, because we don't want to get it wrong. Look here. This is the ammeter. The ammeter is reading the total current. Remember what we said, we haven't got internal resistance, so what we can use is EMF, that value there, and we can forget about internal resistance. We know the external resistance, so we're going to use that formula there. We're going to say let's just do it like this. We're going to say V is equal to I times R, and we're going to substitute into that equation. So I'm going to say V is equal to I times R, and we're going to say that's 12. We don't know I. We know that R was 8. So therefore, change the subject of the formula around, and we're going to get I is equal to 12 divided by 8, which is going to give you 1,5 amps. Okay, I know I've worked a little bit quickly through that one, but try and follow and make sure you've got it. Some people will say, no, I don't like that formula. I would prefer to use R is equal to V over I. Be my guest. You're welcome to use it. You're just substituting in. They're the same formula. There's no problem with using those. Okay, you could even use this one. You could even change the formula and say, I really want to show the examiner that I'm remembering that EMF is equal to IR plus I little r. And then substitute into this and say the current is what I'm trying to find. That one is 8. This one is the one I'm trying to find. But this one is 0. And this one was 12. So I could do it that way. I've just done it a step ahead. Okay. Abram, are there any questions so far?
I have a lot of questions for you, Johan.
Okay. I tell you what. I'm going to leave the next part of the question, this part. He then connects a voltmeter across various points. I'm going to leave that for them as a challenge, and let's see if we can answer it on Facebook. If we've got time, we will. What we're going to do is basically work out V is equal to I times R in each case. Okay?
Yeah.
But let's go with the questions.
All right, here's the first question. On the previous question, Gatsby says, where did you get the 0,5 in the small r?
Okay? I did try and explain this a couple of times. Notice what it says. Each cell has an EMF of 1,6 and an internal resistance of 0,25. And then what did we go on to say? How many cells have we got? How many cells? There's
2.
1 cell. There's 2 cells. So we've got a total resistance of 0,25 times 2. And that is 0,5 ohms. Okay. Got it?
Mm-hmm.
Make sense?
It does.
Okay.
Hope
I hope
it
you've
makes-
got that at home. Any others?
For now, let's just take one from Connie.
Yeah.
Msov says, let's assume that the current now divides to both the resistor as they are in parallel. Can you show the reading at the resistor with 10 ohms?
Was it on this one? Oh, yeah, okay. Okay, very good question. Now, guys, what you need to know is that the potential difference, and I haven't got time to do this in total, the potential difference across that is going to be the same. So you can work out the current going through each of these separately using Ohm's law, and you will get the answer. Okay, it's not, remember, the smaller resistor takes the bigger current, and you can do it by proportion as well. Okay.
Thank you so much,
Okay,
John.
pleasure. That was a bit of a rush on that last one, and I'm sorry, I don't think I've explained it fully. I will post it on Facebook as well.
Please do. And otherwise, Mindsetters, if you still need some extra help, feel free to visit our help desk on our website, which is on mindset.co.za/help desk. We'll be so happy to help you out. Otherwise, even on Facebook, we're there to assist you. But from us to you, we just want to say thank you for taking your time and learn with us. See you some other time. Peace.